Right, so what I want to look at here is the concept of acid-base reaction. So we've done a bunch of exchange reactions, and we kind of know how to write the formula or the reaction equations for that. So we use the Bronsted-Lowry theory and the idea of proton transfer, whether or not it is in water or not. This is something that will occur. But most acid-base reactions are in aqueous solution, and they usually produce a salt plus water. So that is what you sort of memorize, hopefully have memorized by this point. But these reactions are, like I said, exchange reactions. In other words, we can look at an acid-base reaction as HCl, aqueous, reacting with sodium hydroxide, which is also in aqueous conditions, to form water and the salt. And of course, the salt is the combination of the sodium and the chlorine that swap partners. In other words, the salt is sodium chloride in solution. Now, you're well aware of the fact that once we place HCl in water, what actually happens? In other words, what does aqueous HCl do when it's placed in water? We know it will immediately, because it is a strong acid, so that's the important part. It's a strong acid, so it will completely ionize. And what will it completely ionize to? It will form hydronium cations, so also in solution, and chlorine anions, also in solution. In other words, we can actually look at HCl in aqueous solution as H3O plus and Cl minus. So when you see, let me just rub out the, oops, I forgot that we'll also do that. Sodium, Cl, the bracket. So what we can actually do is we can think of HCl when we see that. So it's a strong acid. So for any strong acid, you can do this. You can see it as a combination, given that it's in aqueous conditions, a combination of the anion with hydronium. So how does that change our perspective of this reaction that we just looked at? So if we write, instead of HCl, and we write H3O plus Cl minus, and we split everything up into their ions. So HCl becomes H3O plus. So everything is in aqueous conditions, so I'm not going to write that out every time. The sodium hydroxide is a strong base. In other words, it also splits easily into its ions, forming water. Water won't split into anything because that's a pure compound. And then there's sodium ions plus chlorine anions. So how do we write a net ionic equation for this? Well, we look at what is on both sides. So we see there's a chlorine on this side, chlorine anion, and there's a chlorine anion on this side. We see a sodium, and we see a sodium. And the others are just there. So if we write net ionic equation for that, so net ionic equation, we will get H3O plus, which is of course in the aqueous state, plus OH minus, also in the aqueous state, to form water. Meaning that if we have a strong acid, and specifically with a strong base, this will always be our equation. The only thing that is really of matter is the fact that the hydronium cations will combine with the hydroxide anions to form water. So this, as I say, is always the case for a strong acid reacting with a strong base. So when you see that, you know it's a strong acid. Or when you know you're combining the two, you will know that immediately is the net ionic equation. And that's why they're called neutralization reactions. Because the solution ends up neither as acidic or basic. So if you have a mole ratio of 1:1 of your acid and your base, or just the balanced acid to base ratio, you neutralize all the acid and you neutralize all the base, and you have a solution with a pH of 7. And of course, we'll look at pH a bit later on. However, the story changes. So now we looked at a strong acid, strong base. What happens when you have a weak acid with a strong base? So the weak acid that we will look at is acetic acid, so CH3CO2H. It's dissolved, it's an aqueous state, plus sodium hydroxide, so sodium hydroxide, also in the aqueous state, producing what? So what is the base? Sodium hydroxide is obviously the base. It will deprotonate the acetic acid. And well, we know there are exchange reactions. In other words, this H will go there, and the sodium will go there. Now we get CH3, CO2, sodium, dissolved, plus HOH, which is H2O, a liquid. You should be able to recognize that anything containing sodium normally is dissolvable in water. So we can split this, or can dissolve in water. I don't think dissolvable is a word. So we can split this up into CH3CO2 minus aqueous, plus sodium cations, aqueous. Now, since acetic acid is a weak acid, we use the molecular species on the left-hand side. So what did we do for HCl? For HCl, we said, you know what? HCl splits into hydronium and chlorine anions. But here, we don't say acetic acid reacts with water, producing two ions, and that reacts then with sodium hydroxide. So we leave it as a molecular compound, and a molecular compound meaning it remains as written. So where do you check whether or not something is strong or weak or whatever? You can go back to a table that we had earlier on, table 3.1, where you're able to check what are strong acids and what are strong bases and so forth. Okay, so you'll study which ones are strong and which ones are weak. So to write a complete net ionic or complete ionic equation for this, we will then leave the acetic acid as is, CO2H. So I'm just going to leave out the phases for so we can get through this a bit quicker. Sodium hydroxide is a strong base, so it splits into its constituents. And that then forms sodium. Well, we know from here, so that thing splits, the sodium acetate splits into its constituents because it can dissolve in water, CO2 minus plus water. Okay, now the question is, what are the spectator species? So there's acetic acid on this side, there's no acetic acid on the right-hand side. So you look exactly, it needs to be exactly the same. There's a sodium here, and there's a sodium there. So that can be eliminated. Hydroxide on the left, there's no hydroxide on the right, and water is also just on the right. So in other words, our spectator ion is just the sodium ions, and our net ionic equation in this case is CO3 2H, which is dissolved, so in the aqueous state, plus OH minus, giving us CH3 3 CO2, oh, this is of course aqueous, CO2 minus aqueous plus water. Which is a liquid. And what do you notice is the difference between this net ionic equation and that of the strong acid and base reaction? You notice that the actual acid is there. There's still an OH, it's the same, and that forms the anion and water. So we have two additional things, if you want to put it like that. So for the weak acid, we have its anion version still there, and its molecular version still there, which is not present here, right? There's no that over here, and that's the difference. So you can read this problem-solving tip. It's quite well written. It says weak acids like acetic acid exist in aqueous solution primarily as molecules. So of course there's going to be a small amount of it that they associate, but not all of it. Whereas strong acids, strong bases, and soluble salts exist as ions in solution. So your difference there is exactly that. We can split up a strong acid. We cannot split up a weak acid. Okay. So let's write the net ionic equation for an acid-base reaction. This question asks or gives a lot of info. It says ammonia is one of the most important chemicals in industrial economies. Not only is it used directly as a fertilizer, but it is raw material for the manufacture of nitric acid, another commercially important chemical. As a base, ammonia reacts with acids such as hydrochloric acid. Write a balanced net ionic equation for this reaction. So in other words, our main words, the question actually only starts here. Up until that point, it was only given some information regarding the question. So what are you looking at? We're looking at the reaction between ammonia, which needs to be in the aqueous state, to react with the acid, unless there's something else important there, unless the acid can also dissolve it. And this is going to give us what? So what does an acid do with a base? Well, it's going to protonate it. So we have proton transfer to that, and then we have NH4 plus aqueous plus Cl minus aqueous. So that's just our initial investigation of the situation. Of course, this is a salt, so ammonia chloride is a well-known salt from which you actually can get ammonia from ammonium. But we know HCl is actually split into something. When you put HCl in water, you recognize it as a strong acid. So what our equation should look like, because remember we're working towards a net ionic equation. So if you look at that first equation, then you would say, yeah, well, that's all that's there. But we always know a strong acid or an acid-base reaction needs to form a salt plus water. We only have the salt here. So how do we get the water? Well, that's going to pop out by remembering that HCl splits into hydronium and chlorine minus. And that then forms, so here goes the hydrogen, goes there. So that the acid is H3O plus, the base is NH3, then forms ammonium in solution, plus chlorine minus, also in solution, plus water. Because if hydronium loses a proton, it just becomes water. So now we have a salt plus water. But we asked for the net ionic equation. So before I do that, let me remind you that this is connected. So that's where the strong acid part comes in. If we had a weak acid, then that wouldn't have really mattered. We could have we could have left with the first equation, basically. But since it's strong, we need to look for things that are the same. So on the left-hand side, we have NH3. There's no NH3 on the right-hand side. On the left-hand side, we have H3O+. There's no H3O+ on the right-hand side. On the left-hand side, we have chlorine minus, and we have a chlorine minus on the right-hand side. So those two cancel. So in other words, our net ionic equation, so net ionic equation is then NH3 aqueous plus H3O plus aqueous given NH4 plus aqueous plus water. And that's our net ionic equation. So again, ammonia, weak base, so it won't split into weird stuff. HCl is a strong acid. It does indeed split, but that's why we don't just have H3O plus OH minus giving us water. We will have different kind of things on the left and the right hand side. So see the symmetry here in NH3 uncharged, NH4 plus with your acetic acid and the acetate and iron. So you're always looking for something like that. You have to have the species and one of its protonated / charged versions. Now, I've constantly hammered on the point that acid-base reactions or reactions need to have things in the same state. So both things need to be dissolved for the reaction to actually be able to take place. But there's a specific type of reaction whereby you're able to dissolve a solid metal carbonate or metal sulfate or metal something containing a metal in acid. And then by dissolving it in acid, you have byproducts that form. So metal carbonates, for example, so something that has a metal and a carbonate is able to form a gas. It forms gas, and that gas is CO2, because, you can see it's sort of already there. So there's CO2, 3, and CO2. So that will come from it. And just so that you know, all the types of gas forming reactions that you can have is given here in this little table. So metal carbonates reacting with acid gives us eventually CO2. If you have a metal with sulfur, so metal sulfide, you will form H2S. So just follow the pattern. If you have a metal with sulfite, then you will form SO2. And then finally, if you have an ammonium salt, so in other words, something that contains NH4+, then if you react that with a base, you can get ammonia. Okay, so what is it? Metal carbonate with acid, metal sulfide with acid, metal sulfite with acid, and then which one is the exception? Ammonium with strong base. Okay, so just remember that. And these things, so the reason why it forms CO2, so we can quickly look at that. If we have our calcium carbonate, so I'm going to start over here. Calcium carbonate in the solid phase can be dissolved by an acid. So it reacts with acid. So I'm giving you the balanced equation already, but you would normally say calcium carbonate plus HCl. What are acid base, or what are these type of reactions? Remember something like calcium oxide. We did it way back here somewhere. Can't remember. There we go. basic oxides are usually something that have a metal with an oxide. So metal oxide, so like calcium carbonate, there's some sort of connection there, is basic, and HCl is an acid. And then we have an exchange reaction. So in other words, if the Cl goes there, carbonate goes there, we have calcium chloride, but there needs to be a 2, so, and calcium chloride is soluble, so you know it's in an aqueous state, and we will have H2CO3 also in the aqueous state. But H2CO3 is extremely unstable, so it quickly decomposes to, okay, so H2CO3 quickly decomposes into water, which of course is always a liquid, plus CO2, which is a gas. And if we substitute, or we sum these two equations, so equation 1 plus equation 2, so 1 plus 2, we notice on both sides, so on the left-hand side, we have the hydrogen carbonate. On this hand, on the right-hand side, we have hydrogen carbonate. So in other words, they will cancel in the final equation. So calcium carbonate plus 2HCl will form calcium chloride. You can of course write it as calcium 2 plus 2 chlorine minus, because it is dissolved, so it will split into those two, plus the water that's formed, plus CO2, which is of course a gas. And that's why they're called gas-forming reaction, because it forms a gas. Okay, so you can see how you can recognize these reactions. So you're looking for something where this intermediate will form, this intermediate will form. Immediately that is a gas. So in other words, in this case, it's already a gas, so you don't have to worry about that. And then something where you have that kind of situation. So just look for those and then you should be fine. All right, so let's look at a gas-forming reaction. It says here there's a reaction that occurs between nickel carbonate and sulfuric acid, and we need to write a balanced equation. So this, the molecular formula for sulfuric acid, of course, H2SO4. And for nickel 2 carbonate, so carbonate is CO3 2 minus, and nickel 2, so the 2 there means, of course, it is nickel 2 plus. And if it was, then it will be just NiCO3. So NiCO3 in the solid phase. Why is it solid? Because it is a metal carbonate, so, and it can only be dissolved by acid. If you have a strong acid, H2CO, that's going to be aqueous. This then forms nickel sulfate, plus what? H2, remember? So it's an exchange reaction. So the carbonate goes there, the sulfate goes there. CO3. And we just said, well, that thing is very unstable. So H2CO3 aqueous will split into water and carbon dioxide, gas. So again, we say equation 1 plus equation 2. And what's on both sides? This is on both sides. So those will cancel and the rest stay there. So in other words, we have nickel carbonate plus H2SO4 in the aqueous state, which will form the soluble nickel salt, so nickel SO4 aqueous plus water plus carbon dioxide. All right, and as always, you're more than welcome. You can write this as SO4 2 minus and nickel 2 plus, because in principle it is dissolved, so neither right nor wrong. Right, so that's what I wanted to check here. Just go through the idea of the gas forming reactions and acid-base reactions and why there's a difference between a strong acid and a strong base and their net ionic equations. Okay, thank you for watching.